So we start with the concept of a dot product. It's something we have for three-dimensional vectors. And this time we will look at the dot product from the n-dimensional perspective. So from the n-dimensional point of view, if you have two vectors, A and B, quite general vectors with quite general components from A1 to AN, normally in the n-dimensional scope, in the n-dimensional setting, we define the dot product. Look at this, how we do that. Dot product of these two. I'll make some, maybe you'll find this a little bit unexpected, but I'll put it like this. I'll put it like this. You see, so I treat my vectors as matrices, and I now see what I did? I just converted my A matrix, which was a column. I got n rows, one column matrix. I transposed it, and I multiply with the B as a matrix, and this dot, this is the regular matrix multiplication. If I sub in the vectors itself, it will be something like this. Look at this. This is a transposition of A matrix, which was originally the vector, but we were looking at it as a matrix, and that's the matrix B. If you do the way we multiply the matrices, so you take the row here and you per component multiply with the column here, you will end up with the matrix of size 1, 1, right? That's how if we multiply two matrices of rectangular size, of compatible sizes, the result would be a matrix which has this many rows and this many columns. So it's 1, 1 matrix, which we can identify with a number, and that's the number which we call the dot product. It's a little bit new, it's a little bit different angle of looking at the dot product via the matrix multiplication, but essentially this is the same as we had before. So if you do this kind of tree, if you do this matrix multiplication, you will find out the formula for that, which is this one. So you multiply this per component way, BA1 with B1, A2 with B2, all the way down to AN, which you multiply with BN, and you add them together. That's your dot product. I have a quick example here, so I just made it up, this example. So if I have a vector A like this, 1, negative 1, 2, 3. If I have a vector B like this, 2, 1, 1, negative 1. It's a four-dimensional vectors. If I compute my dot product, 1 times 2, this one with this 2, negative 1 with this 1, this negative 1 with this 1, 2 with 1, this 2 with this 1, and 3 with negative 1. And surprisingly, the result is 0. So we just, I think we can check this easily. 2, take 1, plus 2, take 3, it's 0. Dot product has a few properties which we will use this, or you will use these properties in this topic and in any other, in any successive topics. You will use these properties most of the time without even paying attention explicitly to that, because they are so natural, so expectable. There isn't much to say about this, but I'll just mention them here. Your lecture notes have them. I have 3 of them here on this slide. I have 3 of them. One of them is the dot product, unlike matrix product. You see, I introduced my dot product using the matrix product, which by itself, matrix product is non-commutative thing. You're not allowed freely swap the factors. But for the dot product, actually you do have a commutativity, so it doesn't matter in which way you compute the dot product. You have this sort of distribution law which connects dot product with scalar multiplication, which is like so. By the way, it doesn't really it's not said explicitly in this writing, but actually you have to realize that I have 3 dots here, right? This dot, and this dot. But these 3 dots, they actually have completely different meanings, each of them. For instance, this dot, it's a dot product. This dot product, which is introduced. This dot, it's again this dot product. But this dot represents scaling, which is effectively not the scaling actually. This actually there is if I use dots everywhere where I can, there must be another dot here, and that would be scaling. But this dot, what's this dot represents? Right? Matrix. What's this? What kind of what kind of nature this element, this symbol? Number. What kind of nature is this bracket? Number. Number. It's a number. So this dot effectively is just a numerical product. It's just a numerical product. So here you're looking at the numerical product, here you're looking at the dot product, here you're looking at the scalar multiplication of vectors with a number, here you're looking at the dot product again. So one single dot, but it carries different meaning in different contexts. And the third one is, it's a distribution law. So if you dot product a vector with the sum of the other two, you can alternatively dot product the vector with B and with C and then plus them together. Again, if I just draw your attention to this pluses, for instance, this plus and this plus, although I use the same symbol, it's two different pluses, essentially. This is the plus between the vectors. This is the plus between numbers. With dot product, you have two geometric concepts associated with the product, with the dot product. One of them is the length, the other one is the angle. We will discuss both of them because if you think about this, dot product is the only way to approach these two purely geometrical concepts in n-dimensional setting. I mean, when you live in the 3 dimensions, of course you know what the length is, what the angle is, but as soon as you start moving to the higher dimensions, you can't see this, you can't picture this. So the only way to approach to these two things, geometric things. Hi, you said hi, right?
Hi.
Yeah, hi. Dot product is the only way to approach these two things in higher dimensions. So with length, it's actually, that's the way how we approach length in n dimensions. So we take root of the dot product of the vector with itself. If you do your dot product in a per component way like this, the result of that will be this one. So here's the length. I just gave you one simple example. I'll just give you one simple example for this B. It's just very simple, straightforward computation. For the B, you just do the sum of squares. 2 square 1 square 1 square negative 1 square, which makes it root 7. That's the length of B.